Hello and welcome to Chemistry with Dr. Clark. In this video, I'd like to talk about reaction quotients. Now, I've split the video into two parts, a part one and a part two, because in the first part, I'd like to talk about the theory behind reaction quotients, and in part two, I'd like to do some calculations based on reaction quotients. So if you need both theory and some practice, you'll want to watch both parts. If you're only looking for some calculations, just maybe part two. And I've got a link to part two in the description below. Now, the other thing is this here is very much based on solubility product constants. I do have a few videos that cover that. So if you're not feeling 100% confident about your solubility product constants, your KSPs, it might be worth your while pausing this and going back and watching a couple of videos on KSP. Okay, that'll help you quite a bit. Okay, now before we do start the reaction quotients, maybe we should talk about solubility product constants just briefly. So if I have a substance that really doesn't like to dissolve in water, okay, silver chloride is a perfect example. If you take some silver chloride and you put it into some water, the majority of it will sink to the bottom of the container and sit there as a solid. Okay, this stuff does not like water. But a very small amount of it will dissociate, will break up to form silver plus ions and chloride minus ions, which actually do get dissolved in the water. So the majority stays as the solid, but a very small amount dissociates and breaks up to give you silver plus and chloride minus. Now it is an equilibrium. So eventually, for every one silver chloride that breaks up, there will be one silver and one chloride that reform back into a solid. So break up, reform, break up, reform, and you get an equilibrium. So let's say that we want to talk about the equilibrium expression for this equilibrium. Okay, so KSP is our equilibrium constant. If you have something that doesn't like dissolving in water, okay, we give it the special name solubility product constant, but it's still just an equilibrium constant. And when you're writing out your equilibrium expression, it's always products divided by reactants. So my first product is a silver plus, so Ag plus. Now, there's a lot of different things you can know about the silver. You could know its mass, or its volume, or a whole number of things. But the thing that we really want to talk about when we're talking about equilibrium expressions is its concentration. Okay, I want to know the concentration of the silver plus. I want to know the concentration of the chloride minus. And to show that we are dealing with concentrations, we put a square bracket around it. Now, this equilibrium here is completely balanced. Okay, for every one silver chloride you have, it'll break up to give you one silver and one chloride. Now, the numbers used to balance the equation are important because they do show up in my equilibrium expression. If I use the 1 to balance the equation in front of the silver, in my equilibrium expression, that becomes a power of 1 times. Now, I do have a second product. The second product is a Cl-. Again, I want to talk about its concentration, so nice square brackets. And the number used to balance the equation in front of the chlorine, or chloride, is a 1. Therefore, the power is a 1. Okay, so you had two products. They're both in your numerator. Now, at this point, normally you draw a line here and you talk about your denominator. You talk about what goes in the bottom. The reactant goes in the bottom, and your reactant is silver chloride. However, in this particular case, your reactant is a solid. Solids are not included in equilibrium expressions. So even though this should be a line and silver chloride in the bottom, because the silver chloride is a solid, we leave it out. So this here is your equilibrium expression. Okay, so let's label it. This is my equilibrium expression. Now, it's important here. This whole thing is called an equilibrium expression. This thing here is called an equilibrium constant. And if you were going to put concentrations in here to do the calculation, these would have to be equilibrium concentrations. Okay, so an equilibrium concentration goes in the equilibrium expression, and it equals the equilibrium constant. Okay, this here whole thing is about equilibrium. So if you're going to do problems that just involve KSP, everything is equilibrium, equilibrium, equilibrium. Now, there's a small problem with that, or some issues. Okay, you put the silver chloride in the water. The majority of it goes to the bottom and sits there. A small amount breaks up and forms silver plus and chloride minus. How do you determine the concentration of the silver plus in the water and the chloride minus in the water, right? That can be very difficult because not all of it dissolves, right? If you put in 1 gram of silver chloride, 1 gram does not dissolve, right? A very small amount does. So determining the concentration of the silver plus and the chloride minus at equilibrium can often be a difficult task, okay? So what we say to ourselves is, well, what about if we didn't use the equilibrium amount? What about if we just talked about the amount we started with, right? So if we come over here, I have the same equation. So if we write the same kind of expression, I could talk about how much silver I have, concentration, power of 1, but instead of at equilibrium, let's say that I talk about the amount of silver plus that I have at the very beginning. Okay, so this is not the equilibrium amount. This is the amount I just added. And if we talk about the chloride the same way, Cl minus, power of 1. Again, this is not the equilibrium amount. It's the amount that's like there at the beginning. So you can see it's a bit of a parallel between the two, right? In my equilibrium expression, I had concentration of silver times concentration of chloride. I can still talk about concentration of silver times concentration of chloride, but if it's not the amount at equilibrium, then I can't call this an equilibrium expression. I can't set it equal to an equilibrium constant. So what we do is we set it equal to a thing called the reaction quotient. So this is our reaction quotient. Solubility product constant, reaction quotient. Okay, they are not going to be the same thing because this is when your concentrations are at equilibrium. This is when your concentrations are at some random time. Okay, again though, the denominator is gone because this is a solid, right? We don't include solids in reaction quotients. And instead of calling this an equilibrium expression, we just call the whole thing our reaction quotient. Now, really the reaction quotient is this, but often we refer to the entire equation as our reaction quotient as well. Okay? This one here only occurs at equilibrium. This one here occurs at any time you want. Now, the other difference between the two. Here, if you have a beaker filled with your water, basically we would take some silver chloride, solid, and we would just throw it in and let it dissolve. For this one over here, basically the silver and the chloride are coming from two different sources. I've got a beaker here with a whole bunch of chloride in it, already dissolved. Okay, it did not come from silver chloride. Maybe it came from sodium chloride, and sodium chloride loves water. So I've got a whole bunch of chloride already pre-dissolved. And the same thing with the silver. I've got another beaker filled with water with a whole bunch of silver already dissolved, right? Maybe this came as silver nitrate. Silver nitrate loves to dissolve. So I've got a bunch of pre-dissolved silver that I'm going to pour in. I've got a bunch of pre-dissolved chloride that I'm going to throw in. And what I want to know is, when I put them in, is it less than the maximum amount, more than the maximum amount, or am I putting in the exact amount to make an equilibrium, right? Because over here, for this equilibrium, there is a certain amount of silver and a certain amount of chloride that can exist in this water, right? There's a certain amount of silver plus and chloride minus. The most of it will sit in the bottom as a solid. So over here, when I put in the silver and the chloride from two different sources, I got like 3 options. You could, if you're really lucky, put in the exact amount of the two so that you have just the right amount of silver plus and chloride minus, like just the right amount. Now, it could be that when you pour them in, you're pouring in less than you can have. So if you pour in less than you can have, you have an unsaturated solution. Okay, so you've put in some, but not the maximum amount of silver plus and chloride minus. If you're really lucky and you did put in the maximum amount, so that the amount of silver and chloride is the same for both of these, then what you have is a saturated solution. You've put in the maximum amount of silver plus and chloride minus. Now really, what's the chances that you're randomly going to choose an amount of silver and you're going to randomly choose an amount of chloride that when they go together, you have the perfect mix? Not going to happen, right? That's really high up on the randomness scale, right? It's probably not going to happen. What's more likely is you'll put in less than the maximum, so that's unsaturated. And if you're unsaturated, that means you've got less than the maximum amount. So all of the silver you put in, all of the chloride you put in, they will dissolve and be perfectly happy. And in fact, you could add more if you wanted to. What's more likely to happen, though, is that you've got too much silver and you got too much chloride. So when you put them in, you've got way too much silver chloride in here. And if you've got way too much, that means some of it's going to have to fall to the bottom as a precipitate. Okay, so it'll fall to the bottom as silver chloride solid. Okay, so this one here, usually the cation and the anion are coming from the same place, right? You've got silver chloride, which is the source of both the silver and the chloride. When you're talking reaction quotient problems, though, the silver and the chloride are coming from two different sources. That way you have a lot more possibilities of how much you're adding, right? Lots of silver, a little bit of chlorine, a little bit of chloride, lots of silver, right? Possibilities are endless. And basically, you could add less than the amount possible, exactly equal to the amount that can dissolve, or more than the amount. Okay, and no matter how much you throw in, it doesn't matter if this is at equilibrium or not. You're going to use the concentration of the chloride right at the beginning. You're going to use the concentration of the silver right at the beginning, and you're going to calculate a Q. This Q will not be the same as the K unless you have magically put in the exact right amount that'll dissolve, which never happens. Now your question should be, I understand why I might want to calculate this, because the KSP is related to maximum amounts of the ions that can dissolve in water. Okay, that's quite useful. But over here, if I'm allowed to choose just any random amounts, that means I'm going to get a random Q, right? If you add a little bit more silver plus, your Q is going to be bigger. You add a little bit less chloride, your Q is going to be smaller, right? This Q is going to be different for every single problem that you do. There's no consistency. So why do we want to talk about the Q? Because, let me skip the extra page there. It allows us to predict if I add two chemicals to the same container, have I added less than the maximum, or more than the maximum amount? If I add less than the maximum, it'll completely dissolve. If I've added more than the maximum, though, I've got too much, then you're going to get a precipitate. So when you're doing reaction quotient problems, and if we go back, the way that you recognize that they're a reaction quotient problem is because it'll always ask, please predict whether a formation like a precipitate forms, right? Predicting for precipitate formation, or please predict if a precipitate forms, or will a precipitate form, right? The question is always about, is there going to be a precipitate or is there not going to be one? Okay, that's how you know that you have this problem. Now, if we do talk about this, if I put in too much of the silver and too much of the chloride, then I'm going to get a Q that's too big, right? It's going to be way bigger than the K. So if my Q is bigger than K, I've put in too much, so a precipitate forms. If I put in exactly the right amount, right? If I put in the exact right amount of silver and chlorides, then the Q and the K will be the same. Okay, so if you've got K and Q the same, you're at equilibrium. That's not going to happen. If, though, you put in not enough of your silver and not enough of your chloride, then these two numbers are too small, so your Q is going to be smaller than your K. Okay, so if your Q is smaller than your K, there's not going to be a precipitate. In fact, you could probably add more of the cation and the anion. Okay, this here is extremely important. Okay, it's worth sitting down and memorizing them if you have to do reaction quotient problems. If the K is less than the Q you've calculated, there will be no precipitate. If the K is smaller than the Q, then you will form a precipitate. Now, if you think back to any sort of chemical mixing that you've done or observed in your science, okay, the ones that we love to do is where you have a solution that has nothing in it, right? It's just purely dissolved. And then you have a solution over here that's also purely dissolved. And then you mix them, and magically a solid appears. Usually it's like a yellow solid or a white solid, but it'll be this solid just magically appears. And it's because you have this. Because you are adding your first ion, you're adding your second ion, and together you have too many of them. And if you have too many of these ions in the water, they're going to have to come together, form a solid, and settle to the bottom. Okay, so this here is worth learning. Now, in part 2 of the video, I am going to talk about some calculations. How do you actually calculate your Q, and then comparing it to the K. So I hope to see you in part 2 of the video series, and as always, thank you for joining me here at Chemistry with Dr. Clark.